now. We talked about networks on Thursday, and then we talked about parallel stuff on Tuesday. Did anybody have any outstanding questions before we get into the homework?
I have a question about initializing the models using the parallel context from that lecture.
Yeah.
So you mentioned, I think, at the time that there was h.std init.
Yeah, you don't need that. That's not special.
Okay.
Yeah.
Okay, that was basically my question, but you'd also said to use that and not f-initialize specifically. Is there a reason for that?
No. Oh, no. So in other words, ignore that. So okay, so here's the deal. Historically, NEURON had this thing. If you look at the NEURON book, which is now 13 years old or something, 15 years old, there was this thing called the standard run system, and so std init gave ways to plug into things using oak, but then you had to actually explicitly call it, and it used this global that we saw, this h.vinit. So now modern NEURON doesn't need any of that stuff. There are ways to do the same thing without that. So you create an f-initialize handler, and then so you can just plug in as many separate things. You don't need to overwrite functions. You don't need to do anything. And frankly, that was mostly a very old legacy on my slides that if you listen to me get confused as I was presenting them, yeah, it's fine without it.
Okay, cool. Thanks.
Yeah. So I guess any other questions? So Ted, would you like to start by discussing the homework from last Thursday?
Sure. Let me share my screen here. Okay, so we had an exercise which was basically to use a very simple model, single compartment model cell, and to essentially drive it with some synaptic inputs. And the first pass on this was supposed to use a passive model cell. And the task was to adjust the weight of the netcon so that the EPSP observed in the middle of the model cell was had an amplitude of 1 millivolt. And the second part of that portion of the exercise was to uninsert pass and insert Hodgkin-Huxley. Now, you don't literally have to use the uninsert command. You could simply build a completely different model cell, or at least one that doesn't have pass but instead has Hodgkin-Huxley. And that's probably the best way to go, rather than doing uninsert and then reinserting other stuff. So I perhaps didn't phrase this felicitously, but the task then was to find out what weight would elicit a spike, the minimum positive weight, and again, 2 significant figures as usual. And what I decided to do, since these look like awfully similar tasks, it's basically the same task. You're taking a model cell and you're attaching a synapse to it, and then you're driving the synapse with an event and adjusting the weight of the synapse. I mean, that's it. Regardless of the model cell, it's the same task essentially. So my implementational strategy is always to figure out how to avoid having to reduplicate effort, and how to make it easiest to manage code. So what I decided to do was write a script that would work with different model cells. So I decided I would implement a passive cell class with some Python code and save it to a file called passcell.py. And I would implement a cell class that was identical anatomically and biophysically, except that instead of pass, it would have the HH mechanism, and call and save the code for that cell class in a file called hhcell.py. Now, in both cases, the cell class is called cell, uppercase C-E-L-L, which makes it easy to write plug-and-play code, which you'll get to see what I mean by that. Then I wrote a script in Python that imports the definition of one of these cell classes and then creates an instance of it and then sets up parameters to run a simulation. And since these are cells that have different properties, the parameters might be different, and so therefore the parameters are cell class specific. But it would have common instrumentation. That is, both of these models, in both cases, I want to attach an expsin to an instance of this cell class, whichever class it is. I want to drive that expsin with events that are generated by a netstim. And in case of vector recording, if I was to do vector recording, I want to be able to record whatever potential I wanted to record, or whatever signal I wanted to record, whatever it is that was a common portion of the task, all right? And also simulation flow control, because basically what we're doing here is if we're trying to find out what EPSP elicits a spike, what input, what weight elicits a spike of 1 millivolt peak. Well, if we're going to do that once or twice, we're going to be doing that in an exploratory manner. And we don't have to think about writing automated code, which is automatically going to incrementally adjust synaptic weights through some algorithm and run many simulations until we get the desired result. We can just do this manually a couple of times and be done with it. So, that's what this netx1.py file does. So let's take a look at actually what's in this file. Some of these files here. And so here's my directory with some source code. Let me make the script in here a little bit bigger. 11. Okay. Okay. So now we're looking in here and we're going to see, well, let's just see what my definition of the passive cell class is. So let me do less pass cell pi. Let's take a look at it. So I start out with a comment. So it's easy for me to find out what is this file about. I import a couple of things that I need. Python isn't going to know what to do with h.section unless I import h. And I want my cell to be 10 microns in diameter and have a surface area of 100 square microns. So I'm going to have to use the constant pi at some point. So I imported pi from NumPy. And then comes my class definition. Okay, so this is all very familiar by now. Only I structure these things a particular way, kind of following the way the cell builder does it. So the first thing I do is I create topology, which is all the sections and how they're branched and connected together. And then I have the statements that specify geometry of the sections, which means diameters and lengths and spatial discretization, although it's arguable maybe that could be deferred until after biophysics has been executed. Then I take care of the biophysics properties, the biophysical properties of the cell class, in which case what I'm doing is just inserting pass, and I'm setting the passive conductance to the appropriate value for the exercise. There we are. Conductance of 5e to the minus 5 Siemens per square centimeter, and EPAS of minus 65 millivolts, which is, in fact, yes, what we wanted for this particular model cell. And the rest of it is just the usual cell class boilerplate, which Robert has shown you and which you've worked with already. So that's the passive model cell's definition, the passive model cell class definition. Okay, I have a Hodgkin-Huxley cell class. We can take a look at that. And again, it starts with a comment. We're importing H and pi because we need them. And then we have the cell class definition. Again, it's topology, creating a soma, geometry, specifying the diameters and lengths and nseg, and then biophysics. And in this case, I'm just inserting Hodgkin-Huxley. So there are my two class definitions. Very similar. The only real difference is that one has got Hodgkin-Huxley, the other one has pass. Okay? So how am I going to use these? Well, let's take a look at netx1.pi. Okay, again, I start with a comment. It's a model cell driven by synaptic input. And since I'm going to be importing different kinds of model cells, one's going to be passive, and I'm going to be just looking to see what EPS, what synaptic weight makes a 1 millivolt spike. The other one's going to be active, and I want to see what synaptic weight makes it trigger a spike, as opposed to just eliciting a 1 millivolt EPSP. So I may have different parameters that I want to load, depending on whether my model is going to be active or passive. And I know I'm certainly going to load a different template, that is a different class definition. If I want a passive model, I simply want to import cell from passcell.py. Okay, and so that's what I'm doing. I start out here with a declared passive model false, but if I started out by declaring it true, let's imagine we walk through this code, declare it to be passive model equals true. When we get up to here, we have a conditional statement. So if passive model, then what does it do? It imports the cell class defined with the name cell defined in the file passcell.py. And it defines a parameter called pre-start, which is going to be the start of spiking of the presynaptic cell as 5 milliseconds, and the synaptic weight as 7.2 e to the minus 6 microsiemens, which is what I'm using because I already determined this experimentally. This is what elicits a 1 millivolt EPSP in the passive model. So if I'm studying the passive model, these are the parameters that I want, and that's the template that I want. That is the cell class definition that I want. If I was interested in working with the active cell, the cell that has Hodgkin-Huxley, I would import the cell class defined in HH cell. And I would want a different start time for my synaptic activations. Why would I want that? Well, it turns out that Hodgkin-Huxley takes a while to settle, and I don't want to be fooling around trying to estimate peak EPSP amplitudes above a baseline that's wiggling around. So I'm just going to let the model run for 25 milliseconds, which is plenty of time for HH to settle, and only then will my presynaptic cell start spiking. Okay, that'll be controlled by this pre-start parameter. And for the synaptic weight, I've already plugged in the answer. I've already fiddled with this, tinkered with it. I know that this is the weight that is going to elicit a a 1 millivolt EPSP in a model with Hodgkin-Huxley. There's a different weight that'll elicit a spike. Oops. Let's see, is that correct? Yeah, let's see if that actually works that way. Okay, and then in my code, I want to instrument my cell. That is, I want to create a synaptic mechanism that's attached to it. That's kind of instrumentation, if you like. It's a signal source I'm attaching to the cell. So here's my declaration. This is the common code from here on down. Okay, up to this point, we've been doing things depending on whether it's a passive or an active cell. From this point on, the code looks the same, regardless of whether it's a passive or an active model cell. Okay, so I'm going to attach a synapse to the cell. That doesn't matter whether the cell is passive or active, as long as it has a soma. And its instance is called cell, lowercase c. Then this code will work with it. Okay, and I set the time constant for the xsyn. Here we are, that's the time constant we want, and the reversal potential for it, and we've taken care of its location. And then I create the presynaptic spike source, which is a net stim, and I'm going to start the net stim at a time that's appropriate for the model. Again, if it's a passive model cell, that value pre-start is going to be 5 milliseconds. Our conditional statement took care of that. If it's an active model cell, it's going to start spiking at 25 milliseconds. Either way, I want the same other parameters, okay? Fully deterministic spike train, if it were to generate a spike train, or spike times, I should say. Okay, and then I need a netcon to attach my spike source to my synaptic target. So this is the declaration that does that. It creates an instance of the netcon class, which connects the presynaptic spike source. This is an artificial spiking cell, so we don't have to use a ref V in here. Okay, this is just an artificial spiking cell. We get away without the ref V part. And then the syn is, of course, this synaptic instance we created up here. It has the delay that we want. It has the weight that we chose earlier. And I think my comments are, yeah, I think this is right. This is right. Yeah, this elicits a 1 millivolt spike. Actually, 1 millivolt EPSP in the Hodgkin-Huxley based model, and this will actually elicit a spike in that model cell. So we don't want a spike right now. I just buried this comment there just as a reminder, so when I come back and do the experiment, I can tinker with it and show that. And finally, I want a user interface, and this I created with Neuron's GUI. It just has a run control and a couple of graphs that are going to plot the membrane potential at the middle of the soma, and these graphs will work with anything that has a section called soma, okay? Because that's what their hook code refers to, is something, actually it refers to the default section. And since in this case, the first section that's created is the default section, that happens to be the soma, middle of the soma. Okay, let's see how this actually works. All right, so again, we saw that NetX1 is going to start with our active model. Let me change that. And let me change that to true. Okay. So that it'll work with the passive model. So let me see, Python 3 netx1.py. Ooh, it worked. And there's no error messages. I should go buy a lottery ticket immediately. The stars are with me. All right, let me run a simulation, init and run. And there is a synaptic conductance transient. And there is some kind of a little thing happening in the membrane potential trace. And let me do a view equals plot. And lo and behold, that starts at -65 as the baseline. It's nice and stable. Then we see depolarization that zips up to a -64.00 whatever. That's good enough to be a 1 millivolt EPSP. Okay. So there we go. That works with the passive model cell. Let me quit. Let me exit. And now let me change this. There's a more sophisticated, more sophisticated way of doing this than doing this editing stuff. Could have used a command line option, but I'm keeping it relatively simple. Okay. So now let's go and run the simulation again. Same netx1 pi, but now it should have an active synapse, active membrane. If I do a knit and run, let me see what this looks like. U equals plot. Aha. So we see the telltale wiggle that happens at the beginning of Hodgkin-Huxley model, and then it settles down, and then at t is 25 milliseconds. Actually, at t equals 25 milliseconds, the presynaptic cell spikes. We have a delay. Our netcon has a delay of 1 millisecond. So our our synaptic target doesn't know anything about that spike until 26 milliseconds, at which point its conductance begins to increase. That's when this XSyn's conductance jumps up. And you'll see that I get an EPSP that goes from minus 64.97 to minus 63.97, good enough for government work. And there we have it. We have the model making a 1 millivolt EPSP. And if I want to make it generate a spike, let me do that. So let me say, what should the weight be? 7.0 e to the minus 5. So let me see. NC weight bracket 0 is currently 1.57 e to the minus 5. Let me make that be 7 e minus 5. And now if I run a simulation, I should get a spike. U equals plot. U equals plot here. And if I change the netcon's weight to 6.9 and then run again, I don't get a spike. So I'm correct to within 2 decimal, I have 2 place accuracy on the threshold here. And I've accomplished part 1 of the exercise and actually part of part 2. Okay, I've figured out what synaptic weight will elicit a 1 millivolt EPSP in the passive model. I figured out what weight will elicit a spike in the active model. And I have also figured out what weight will elicit a 1 millivolt EPSP in the Hodgkin-Huxley model cell. Okay? Okay, so the next part of the exercise is to do this. Change the net stims interval to 1 millisecond and let there be a lot of them. Okay? In other words, an inexhaustible amount. We're never going to be running a simulation that generates 10 to the 9th events. Not if we're doing events at 1 millisecond intervals on the average. Setting the net stims noise to 1 makes the net stims events occur at intervals that follow the negative exponential distribution. Sometimes people call that a Poisson distribution. It's a fair to middling approximation to sort of noisy background activity in cells. Now, on the average, neocortical neurons I think in behaving animals, typically, if they're at rest, just sitting around not doing anything, fire at around 10 hertz. So if we have one such cell targeting our model. If we have one presynaptic cell firing at 10 hertz targeting our model neuron will receive, on the average, 10 spikes per second. If we set up a negative exponential distribution of the presynaptic spike times with an expected value of 100 milliseconds, that would, on the average, hit our cell's synapse 10 times per second. If I change the interval to 1 millisecond, that's the same as having 100 presynaptic cells firing randomly, targeting our postsynaptic neuron. And since XPSYN is a linear mechanism, that one instance of the XPSYN class could handle 100 different afferent streams. Or we can take the cheap out and use a single net stim with an average interspike interval of 1 millisecond, negative exponential distribution, and that's going to generate a spike train, which is like the ensemble train that you would get from 100 different presynaptic cells, each firing with its own negative exponential distribution at 100 millisecond interspike intervals on the average. Okay? So this is like having our cell receive excitatory inputs from only 100 presynaptic neurons. Now think about the fact that in pyramidal cells in motor cortex or sensory cortex typically receive on the order of, they're innervated by about 10,000 excitatory synapses. So this is about 100 times less afferent spike activity driving our little model cell. But of course, it is a little model cell. It doesn't have all that extra membrane. So maybe it's roughly equivalent to a pyramidal cell being driven by 10,000 different inputs. Okay, so now what we want to do is we want to run 100 simulations that include 1,000 milliseconds of synaptic input. And we want to capture the number of spikes per run, and we want to generate a histogram that shows us the number of spikes per run. So we're going to bin it into one spike, the bins are going to contain counts. The counts number of spikes per run is going to be the center of each bin. Okay, so if there's 10 runs that produced 10 spikes in the postsynaptic cell, then we're going to have a histogram with a bin centered on 10, and it's going to have a height of 10. And if there's 15 spikes, if there's 11 instances of runs which had 15 spikes, then centered on 15, there will be a bin which is 11 high. Okay, so that's the kind of histogram we're looking for. So I'm going to reuse, I already reused netx1 and these other files to determine the weight that needs to be used to get a 1 millivolt EPSP. But I need a new bit of code. I need a new script in order to generate a run that has 1,000 milliseconds of synaptic input. I want to wait on that synaptic input. It shouldn't start until the model cell has had time to settle down. So it should start after 25 milliseconds and go on to 1,025. So the total run length, each run is going to run for 1,025 milliseconds of model time. Okay, and we're really only going to be interested in these spikes. So that means we're going to be counting spikes with a netcon. We're not recording membrane potential. And since there aren't going to be any spikes before t equals 25 milliseconds, we can just watch the membrane potential of our postsynaptic cell. for positive going crossings of, in this case, I decided to set the threshold at 0 millivolts, just in case there were a couple of spikes really close together, and that might cause the second of a pair of closely spaced spikes to have a smaller amplitude, a significantly smaller amplitude. Okay, so those are my design considerations. And what does the code actually look like that does this? Let me see. Let me look at NetX2, and this is my source code that I use. Let me file. Well, I'll just quit this other thing. Kill it. There we go. So this is what the netx2.py file looks like. Again, I import H in the GUI. I'm importing numpy in P in case I do need it actually. I need it for matplotlib's hist. In fact, I think I certainly need matplotlib mlab, and I need matplotlib pyplot. And I discovered that by reading the documentation of hist, matplotlib.pyplot.hist at matplotlib.org. I'm just sticking with matplotlib for the sake of simplicity at this point. Other people may want to use fancier things from other libraries. They may have other advantages. Okay, so I want something that actually gives me the opportunity to run a few tests before I launch the whole, big task. So I'm going to say, let's just do 10 runs and make sure that things work. Okay. So I declare this parameter right here where it's easy to get at. And now I get down to my code. Once again, I'm going to import the cell class definition from HHCell, which means I'm getting the definition that has Hodgkin-Huxley. I'm creating an instance of that class. And now instead of having a conditional statement, since I know this is an active model, this has Hodgkin-Huxley, I just know I need to wait 25 milliseconds for it to settle. And I also know what synaptic weight, I should say what netcon weight I need in order to elicit a 1 millivolt EPSP in my model cell. So let's take a look at the specification of instrumentation. Oh, it looks pretty much the same as in the previous shorter script. In fact, it's pretty much identical here. And so is this. Only for this part here, pre-interval is now 1 instead of 10. Pre-number is 1e to the 9, and pre-noise is 1, which means that the inner spike interval, the entire inner spike interval, is subject to the negative exponential distribution. Noise is actually a number that can range, a floating point number that can range from 0 to 1, and it specifies what fraction of the interspike interval is going to be random and what fraction is not. If it was 0, none of it would be random. If it's 0.5, then the first half a millisecond is guaranteed to be silent, and then after that, you're going to get you're going to have an interval spike interval to the next spike, which is governed by the negative exponential distribution. Okay, so the most common spike will occur at half a millisecond intervals, and then you'll have negative exponential distributions after that. Okay, so here is our netcons delay and wait as before. Here's our same experimental rig. We got our run control and plots of membrane potential and synaptic conductance. Now, however, we want to record spike times, and to do that, we'll need a vector. So I'm creating an instance of a neuron vector to capture the spike times, and I'm using a netcon to watch membrane potential at the middle of the soma for positive going threshold crossings. and it's not going to have any target. This netcon is not going to deliver events to anything. It's simply, I'm simply using it to get a spike detector, okay? And then of course I have the obligatory reference of the cell section that we're referring to, okay? Here's my statement of what the threshold should be, because again, I want to capture small spikes if any small spikes do occur. I'm expecting most of them, if not all of them, to go over the x-axis, to cross over the x-axis and have maxima that are positive, but we'll just make sure that we don't miss any. And then I have the statement that tells the netcon to record those events to the S times vector.
Ted, we have a question, by the way.
Yes. Where's the question?
Yeah. What is the value you have set? Isn't this for the passive? I mean, for the 1 millivolt EPSP you are doing the value that you have set up above?
Yes, it is. It's to give a 1 millivolt EPSP, and that's what I want. I want a synaptic input that produces a 1 millivolt EPSP. When you get a unitary activation, okay? If the cell is sitting there, the synapse is sitting there, nothing's happening, along comes in a single input event, it gives just enough of a conductance change to elicit a 1 millivolt EPSP in the target cell. Now, if another EPSP comes along 10 milliseconds later, there may not be enough of the first EPSP left over to add up to anything. But if the second EPSP is elicited, say, maybe 2 or 3 millivolts later, I may get addition, summation, temporal summation. Yeah. Exactly. Okay. So again, we're aping what happens in cortex. We're saying, well, we have a lot of presynaptic cells, and they're all listening. All these little tiny depolarizations, and for right now, we're ignoring inhibition. No inhibition in this model at all. And we're saying, you know, what will we get out of this? Will we get plausible amounts of spiking activity or not? And what will it look like? So there we have our specification of the spike trains, and we have our specification of the synaptic weight and latency. Okay. Con pre-syn, good. And we have our same old user interface that we had before. I'm going to have a run control panel so I can launch a single simulation if I want. And it's going to plot membrane potential in the soma and synaptic conductance. Okay. And then it's recording. Right. And then let's see, T-stop. Okay, T-stop pre-start. Okay, yes, we want the simulation to run until 1000 milliseconds after the spike, after the afferent input starts. The afferent input starts at a time which I've already stored in this variable, pre.start, which is a parameter of the presynaptic cell, the net stem. And the run is going to run until 1000 milliseconds. And since I've changed the stop time, I may want my x-axis on my graphs to automatically be the time axes on these graphs to be rescaled. So in fact, that's what the purpose of this is. This statement makes sure that if I am doing an individual simulation, I will see the whole 1025 milliseconds of simulation. Okay. Now, if I were to comment everything out past this point, I could just run a single simulation and that would be fine. But I wouldn't be able to do anything with it. I wouldn't have any data saved. I wouldn't have any graph of the histogram done. So what I did was, first thing I did was I created a function that launches a single run And this is essentially a concatenation of HF initialize and H continue run. Okay, so it's basically those two things being called one after another. And during that run, the S times vector is first initialized to 0 length, and then every time a new spike occurs that is detected, that spike is saved as appended to the S times vector. So at the end of the run, this vector will have a length equal to the number of spikes that happened. The value of the elements in this vector will be, these values will all be the spike times. But I'm really not interested in the spike times in this particular experiment. I just want to know how many spikes did occur. So that's why I'm returning the size of the vector. Okay. And if I executed one run at the command line, it would run a single simulation, and I would be able to print out the contents of the S times vector and verify what the size is if I wanted to. Having debugged this, make sure that it works, my next task was simply to create a procedure, actually a function, that performs a user-specified number of runs and returns a list that contains, whose elements are the number of spikes in each of the runs that was executed. So the first thing that happens on entry to this procedure is it declares that counts is a new list, and then for n times, it does this, which means first thing that happens is it launches a run, and that returns, it does a function call, okay? It calls one run, which returns the number of spikes that were generated in that run, and that value is appended to the counts list. And then it returns counts. Okay, so when I call batch with an argument of n runs, where n runs I've already declared up at the top of the file, for this test purposes I said 10, I will run 10 simulations and I will get back a list called n spikes, whose elements are going to be the spike counts from these 10 different runs. Okay, and if I changed n runs to 100, I would get back spike counts for 100 different runs. Okay, so then I have here the task. Now that I've got those results, I have the task of how to plot. So what I wanted to do is I wanted to know how many bins I want in my plot. I want my bar graph, I want my histogram to have bins that are 1 wide, okay? So these are counts, and I want to know all runs that had a count of 9 or 10 or 11. So I want each bin to be 1 wide, okay? And so I know the number of bins then by checking out my list of spike counts and finding out what's the biggest spike count from any of the runs and what's the smallest spike count of all these runs. And then I know I need, if I take the difference between those, I need to add 1 to it to get the total number of bins that I need. Okay? Now that I have that information, I can call plot hist. And I do it with particular arguments because I want each bin to be centered on a whole number of spikes. If you don't do this, what will happen is it'll be one of the edges of your bin. Your bins have boundaries between them, and instead, you know, the bin for a count of 15 spikes will have its left edge at 15 along the x-axis. Okay, and to me that's not very intuitive. When I look at a bar graph, I expect to see meaningful labels beneath the bins, and if I see a bin I expect to see beneath at least some of the bins a hash mark centered on the middle of the bin that that has a label. It tells me, how many, is this the bin for how many count? Is it the bin for a count of 9? Is it the bin for a count of 10? For a count of 11? Which is it? So I had to use the range argument of the HIST method to shift things over a little bit at each end. If I didn't do this, the bins would look weird. You're welcome to eliminate these minus and plus 0.5s and see what happens when you get, or just comment out the range statement and see what your bins look like, and then tell me that that looks more intuitive than the display I'm getting with this. You'll have a hard time convincing me. So let's actually execute this. Whoa, Python 3 netx2.py and see what happens. Okay, so it took a little longer than it might have otherwise because I'm actually refreshing this graph on each run. But it was kind of reassuring to see those graphs flicker by. And these are the bins. These are the spike counts. For a spike count of 10, how many runs had a spike count of 10? Well, 1 run. How many runs had a spike count of 11? 1 run. How many had a count of 15? 1. Okay. How about a count of 19? 2. All right, well, that's not looking very smooth, but at least it's a histogram, and at least the bin centers make sense. Let's actually take a look at the data that were printed out, because this file actually contains a couple of statements that print out the bin boundaries and the counts in the different bins. Okay, so let's take a look at the source code and see how that is done. Where is that anyway? Oh, the heck with it right now. Let's just, let me just hit return. I can't hit return. Ah, that graph is blocking it. If I kill that graph, I now get back my prompt and I can operate interactively the way I like. I can do an init and run. Okay, and you'll see that each time I do a init and run, I get a different pattern of spikes. Okay, we'll talk about that in a little bit. Is that a desirable thing or not? Let's go back and look at our source code. Yes, thank you very much. Timers cannot be stopped from another thread. So let's go back and look at netx2. And so you'll notice that after the statement that creates the histogram, actually it doesn't show anything. It doesn't plot anything until plot.show is executed. But I made sure to print the bin boundaries and the bin counts, which are returned by this call, by the way. This call returns a tuple. And the 3 things in the tuple are the bin counts, the bin boundaries, and something called patches, which are graphical objects, and I'm ignoring those. Okay, so plot show is what it was that threw up our graph at us, and we could see it. Okay, so now we have walked through this code, and I do have one concern about this. And that is what I mentioned earlier. You noticed how every time I ran a simulation with the init and run button, I got a different sequence of events. Well, this is an example of what Robert was talking about in his network presentation, where he spoke about the use of what I would call principled randomness or reproducible randomness. And his point was that unless you are careful about this, you're not going to know how to reproduce your runs that involve randomness. And the best way to reproduce your simulations is to use a a strategy in which everything that requires randomness has its own pseudo-random number stream, its own generator. And the only thing that we're doing that needs randomness is the firing of the presynaptic cell, the spike times of our net stim. And in this case, I didn't do that. I just allowed that net stim to draw from neurons, old, built-in, and adequate for prototyping, but not what you would want to use for really high-quality work. Its own single stream pseudo-random number generator. Okay. Now, since it's a single stream generator, we can specify a seed for it. We can start it at different points in its pseudo-random sequence. But unfortunately, we don't really have good control. So if we were to do anything else that required randomness and ate up a sample from that pseudo-random stream, then everything else we did past that point would be affected. So we don't want that. We want to have explicit control over our pseudo-random streams, which means we really should be pairing our net stim with an instance of the random class that is generating its own pseudo-random stream. And the best way to do that is with random 1, 2, 3. And in case you weren't paying attention, let me bring you back to his excellent PDF from that parallel neuron talk just last week. Or was it just last week? Was it just Tuesday?
Tuesday.
And just Tuesday, just 2 days ago. Right, a lot. Time flies, okay? And so you want reproducible randomness. You want it to be independent of the number of processors. You also want it to be independent of where things are. Let's say you have a density model. Oh, excuse me. Let me say, suppose you have a distributed model network. And your cells, some of your cells are on one processor, some of your cells are on a different processor, and each cell is doing something, has something going on that requires a pseudo-random stream. You don't want that pseudo-random stream to be affected by which processor it's on. If you decide that for the purpose of, say, improving load balance, you need to redistribute where your cells are placed, you better make sure that you have paired all code that requires pseudo-random streams with that cell in such a way that it ends up on the same processor and that it's initialized in the same way, seeded properly. We have a very simple task here. With this very simple model, you have only one thing that needs pseudo-randomness, but we should take better care with it. And what we could do is we could seed our random stream and let one of these indices be a number that corresponds to how many runs we've done. Okay, so two of these parameters used by random 1, 2, 3 are free for us to do whatever we want with, and the third one could simply iterate starting from 0 and then go on the first run, and then go to 1 on the second run, and 2 on the third run, and 3 on the fourth run, et cetera, throughout all the runs that we're doing when we do our batch run to count spike times. Okay, and by starting it at a defined initial point and iterating it in a very controlled way from run to run, we can then instantiate reproducible randomness that will allow you to produce the same results anywhere on any machine at any time that you run this. So let me see here. Let me quit this. Actually, let me net x2 pi.
And
let
Ted,
me change.
Just to point out, it's now 2 o'clock.
Okay, so that's it. So if I would change that to 100, save it, and batch run it, and I could generate my fancy histogram. I leave that to you as an exercise. And I now quit and let Robert take the reins here. Let me see, stop share.
Do you have time to take any questions, if anybody has any quick questions?
Well, let's see. Looks like you've handled some questions already.
No, I just made some comments.
Well, that was good. That forestalled questions. Anybody have any questions about this so far? If not, if you have questions later on, please contact us or post the questions in Slack. And I'm sure you'll have questions when you start actually using this stuff. Okay, so what I'd like you to do is a homework exercise on this. I'd like you to make this netx2.py treat randomness properly. Okay, use random 1, 2, 3, and pair that with the netstim. Okay, and follow the example code that Robert provided in his slides. Okay. Well, sir.
All right. One last call for questions for Ted. All right. Hearing none, so I want to talk about the exercises from Tuesday. And I think before we do that, I'm going to have a little bit of a spiel on like how we actually run some of these models on our own computer. Like I gave all of this theory about the parallel stuff, but I didn't really, I gave all this, like, this is how we do it in Neuron, but I'm going to say a little bit more about what's actually going on and what it means when we're doing this in parallel and how we launch this. And the other question that I have for everybody before I do this, there's two ways sort of that I see that we can do today. And I've done it both ways in previous sessions. We could, so I have solutions. My solutions to the parallel exercises are posted on Slack in a zip file. You could look at them. So option number one, we could try to do everything together. I do have a strict cutoff of 3 o'clock, so it's more or less the right amount of time, but it's going to be a little tight to do everything. Or we could go through my solutions, and I was wondering if people have any strong opinions, if they'd like to see the thought process and how I go about approaching these problems, or just sort of discuss it from the solutions. Anybody have any opinions?
My opinion is the thought process is important.
All right, I'm inclined to agree. All right, so let me do this. Let me share my screen here because I want to make one other point. So here is desktop 1. All right, and I'm going to use just Visual Studio Code and a regular terminal. I'm going to make a folder on my desktop, 715. 715. Cool. And okay, so what's going on when we're talking about parallel stuff? We had all of this stuff, Tuesdays was a whole discussion, whole lecture about parallel computing and how to do everything in Neuron, but what does any of it mean? So here is what I'd like to show you. So let's just say I create a new document here, and I'm going to, from Neuron import age, that's not going to surprise anybody. We said that any time that I want to do anything in parallel in Neuron, there's a couple of steps that we have to do. So first of all, we have to initialize what's known as MPI. So that's always going to start out with an h.nrn MPI underbar init. Cool. Also, all of the parallel stuff through Neuron otherwise is available within the parallel context class. So we can create an instance of the parallel context class. And in particular, So let's just save this and let's just, where did I put this? Desktop, parallel demo.py. Yes, okay. So in here, I have this file called parallel demo, and it obviously does nothing. And sure enough, if I run it, it does nothing. You will note that it does, however, point out how many processes I am using. And the reason for that, the rationale for that, is just, that's a side effect of initializing MPI. So we'll see that, but normally your standard program uses one process. But as you're no doubt aware, your computer likely has 4 or 8 or some number of cores. And we'd love to be able to, instead of just using one core at one time, to use more. And MPI is a way that not only can we use whatever's on your computer, if we have an HPC system, so Ted, for example, is actively involved with the Neuroscience Gateway, which is a free platform that you can use to run, get access to high performance computing for neuroscience. You know, and everything that we do here that I'm going to present in the context of running on your machine will run just fine in Neuroscience Gateway or your university supercomputers. All right, but here's the fundamental thing. This is what makes parallelism possible. So I'm just going to print out one thing, and I'm going to do this with an F string, and I'm going to say, hello, I am pc.id of pc.inhost. Okay, so what this is saying is if I'm going to tell this, I want to run this in parallel using 4 processes, then in-host is going to be 4, right? And then each process is going to get a unique ID. It'll be, so one of them will think that it's processor 0. One of them will think that it's processor 1. One of them think that it's processor 2. One of them will think that it's processor 3. Of course, if I just run Python parallel demo, I'm going to get yelled at because I put the F in the wrong place. Print, not printf. If I just run Python parallel demo, of course, I haven't told it to use more than one processor. So it's just going to come out and say, well, there's only one process running and I'm process 0. Cool. So how do we tell? So the key thing is that we can tell the computer, we can tell NEURON in this case, that we want to run in parallel using what's known as MPI, or the message processing interface. And this is a standard. This has nothing to do with NEURON. This is what every HPC out there that you're likely to come across uses. If you've installed MPI on your system, so for Windows, there's Microsoft MPI. You can look it up and download it. For other platforms, if you're using Anaconda, honestly, the way that I did it on my system the other day was I just did conda install MPI for Pi, and that was able to give me the Python library MPI for Pi. In particular, it also pulled in its key dependencies, namely MPI. So if you're using Anaconda, that should work, and that should give you a working MPI setup. So how do we actually run, how do we have MPI tell Python/NEURON that we want to do something in parallel? The syntax is we say MPI exec, and then we'll say, so that's say, hey, look, MPI, I'm talking to you. All right, MPI exec -n, and then for number, right? And I want to use 4 processors for doing something. And then, so I've now said I want to use 4 processors, and then I'll just go ahead and say Python parallel demo. And now when this runs, all right, now it says num processors is 4, and you'll notice that my single line of code, right, it's one print statement, but now my one print statement is printing out 4 different things. Why is that? Because it's actually running 4 times. Everybody is the same, right? Everybody's running the same bit of code, but they can tell that they're different because they get a different identifier. And this is the fundamental thing that makes MPI-based parallelism possible. It's just one concept. Everybody does the same thing, but they get a different identifier. So how does that help us? That helps us because, oh wait, does it? How does that help us? That helps us because now if you imagine that I have, let's say, 2 processors that I want to use, I can have them know, oh, well, I can have them say, oh, hey, I'm running a simulation with 2 processors and I'm processor 0, so I'll do half of them, or I'm processor 1, so I'll do the other half. And then so everybody sets up their own little portion of the problem, right? They each know how to construct their part of the problem, and then they just communicate and they work through. Does that make sense? Okay. All right, so that is the core fact of life that makes parallelism possible. But okay, so if there's no questions on that, let's take a look at the homework. So the homework involved creating what's known as a ball and stick cell, constructing them in a loop. And I gave you actually some code to do it in the slides. We might do something slightly differently, but construct a ball and stick cell, get it to fire, construct a loop of such cells, and have it run in parallel. And in particular, see if it runs faster. Well, actually, I don't know if I'd said to do that, but if you don't check to see if it doesn't run faster, then why would you run it in parallel? Okay, so let's do this. So fundamentally, our network is going to be constructed of a certain class of cells. All right, so in Python, of course, let's just go ahead and save this. This is ball and stick. In Python, you know, a class of cells is defined using the class keyword, ball and stick. Cool. So I want to define a class of things. This is what a ball and stick model looks like. And then, you know, every time that you construct a class of things, you need a constructor, and then this is going to describe everything that you're going to want to do. In NEURON, the fundamental concept that we are going to need, so we might as well do this here, is that every cell is going to need an identifier. And the reason for this is because if we have an identifier, you know, then I can talk about cell 5. And then every processor, whether it knows anything about cell 5, it's certainly happy with the concept of, yeah, it's number 5. I don't know anything about it. I don't know how it works, but it's 5, right? 5 is a thing that I can express. I can tell everybody 5. So we can work with that. We can say, hey, look, send a signal to cell 5, or here's something from cell 5. So in order to do this, let's go ahead and assign what's known as a global identifier, or GID. And so then that's a property of the cell. So we'll just say self.gid is going to be GID. Fundamentally, remember we said that we were going to want the point of the ball and stick was that we have a soma, we've got a dendrite feeding in, so synaptic input's going to go somewhere into the dendrite. It's going to be filtered, there'll be postsynaptic potentials, all that jazz, before it gets down to the soma. All right, so we've got 2 things that we need to construct. We're going to need a soma, so self.section is h.section, name is going to be soma, and since it belongs to the cell, we give it the cell equals self argument. We can say the same thing except for the dendrite. Self.dend. Cool. And then, of course, the dendrite should be connected to the soma. All right, and that basically gives us self. That basically gives us the topology of our model. By the way, you'll notice that I have a squiggle under my H. That's because there's nothing that's been defined as H. So from NEURON, import H. From NEURON, you know, and then our usual thing, we might as well grab some units. So microns and milliseconds and millivolts are pretty much always useful. And then, you know, we often like to have std_run.ho because that gives us continue run. So, okay, so now my red squiggle under my H is gone, and I've defined my topology. Okay. So if I've defined my topology, then the next step after topology, anytime you create one of these things is, well, what is the geometry? Right? Well, the soma is going to have a certain length and the dendrite's going to have a certain length and diameter. And so let's just say that the soma's length and the soma's diameter, self dot, his diameter is going to be 10 microns, and that's an arbitrary choice, but this is good enough one as any. And maybe the dendrite's diameter is something smaller, 2 microns, and the dendrite's a little longer, obviously. So in my examples, I did 40 microns, doesn't really matter for our purposes here. Okay, so now we have, and I'm just going to put a little bit of blank space here to separate everything out. We've defined a topology. There's a dendrite and a soma, and they're connected. We defined a geometry. They have a certain length, a certain diameter. We can do our discretization, right? So soma is big. Generally speaking, the soma, you can probably get away with thinking of it as isopotential because current's going to flow through it relatively fast. So let's just say, for the sake of argument, that the soma is going to have 1 numerical compartment and the dendrite's going to have 3. We've seen before that we could come up with sort of a principled way of doing this using what's known as the d lambda rule, which will look at the size and the electrical potentials and sort of figure out about passive conductance and what we'd expect. But this is going to be fine. So we have our topology, we have a geometry, we have a numerical discretization. From the problem, we said we were going to want some ion channels. Well, we're going to want some Hodgkin-Huxley channels in the soma, was my statement, and some passive channels in the dendrite. Remember, we don't need to explicitly add passive channels to the dendrite, to the soma, because the Hodgkin-Huxley channels include a passive conductance as well. All right, and more or less this is it, right? This gives us a cell class. So now we want to actually see if this is going to do anything. So let's just say that I'll create one of these guys. I'll call it cell. Cell is ball and stick. I guess since I have a GID, it's now looking for GID. Let's go ahead and pass in my GID. So I'm going to construct a cell. Let's just save it. And let's just make sure that I haven't broken anything already. So if I type it Python ball and stick, shouldn't do anything. Well, it constructs the cell, but we shouldn't actually see anything. We just don't want any errors. So let's go ahead and run that. Cool. It ran, it exited, it didn't complain. If I wanted to check a little bit more, I could go back and say Python-I, and then that'll give me a prompt, right? And then I could say, well, what's h.topology? And I see, sure enough, that I have a ball and stick that has a soma and a ball and stick that has a dendrite. Of course, this is an awfully, and you'll notice that the soma, these little dashes, well, that's a little bit messy to say, but this dash is indicating that this is of length 1, and these 2 dashes plus this little backtick is showing that it has an inseg of 3. And just to prove this, if cell.inseg was 5, I'll get 2 more dashes when I do the topology. No, I don't. Sorry, not cell.inseg, cell.dendrite.inseg is 5. I'll get 2 more dashes when I do the topology. Right, so each dash and backtick is corresponding to a segment. That's the alignment. It's just a way of visualizing it. The one problem, though, I see very clearly that this one is the soma and this one is the dendrite, but this is a lot of nastiness. You'll remember from, I think, Tuesday a week ago, though, that we saw that we could add a representation function. And so if I just do that, define representation. So how should this cell print out? I don't want Neuron/Python's default of main ball and stick object at some memory location. Because, even if I were to rerun this, I wouldn't even get the same memory location. Just kidding. Let's try that again. Right, so last time it was 0/7FC, now it's 0/7FE. So it's putting it somewhere else. So I'm getting a different display a different name, and that's no good, right? We want reproducibility. So in order to do this, we need to give it an explicit name. And so since we have an identifier and a cell class, let's have our explicit name be the cell class, combine the cell class name and the identifier. So in other words, what I'm going to do is anytime that I want the representation of this object, don't use the default, define underbar representation is going to return, let's say an F string, it'll be ball and stick, and then, in square brackets, self.gid. And now if I were to run this, and I do h.topology, oh, it's ball and stick 1 soma. And if I were to do cell 2 is another one of these things, right? Ball and stick 2. And now I do a topology. I can see, oh, hey, look, there's ball and stick 1 and there's ball and stick 2. And these are how they go together. So that's nice. All right, so any questions about this? All of this we've done before, really. But I do want to make sure people are happy. All right. So in other words, so let's just keep pushing this forward just a little bit further. We want this cell to fire. Ted talked at length sort of about using net sims for doing this. We could do a Poisson process. We could do a deterministic. Let's just do the default's going to be a deterministic. So let's just go ahead and create a net stim. That's a thing that's going to stimulate our network. I mean, there's only one cell, but it's a very small network. We're going to give it 1 spike. And that spike is going to happen at some time, let's call it 5 milliseconds. All right, so there's a stimulus, it's coming in. Where's it going? Well, it needs to go to a synapse. Well, okay. Then there has to be a synapse somewhere. Let's make a synapse a property of this cell. Let's say that all of our synaptic input is going to go into the center of the dendrite. Does that work for people? We could construct mini synapses, but for simplicity. So let's say this cell is always going, no matter how many, for each instance of this cell, I'm going to construct a thing called its synapse. And it will have, let's say, an exponentially decaying synapse that's going to live at the center of its dendrite, or the 0.5 location of the dendrite. And then if I have a synapse, then I'm going to want to have, a reversal potential. So let's say the reversal potential is going to be 0 millivolts, and it's going to have a time constant. So the time constant is, I don't know, let's say 2 milliseconds. That is, in 2 milliseconds, it will have decayed by a factor of E relative to whatever input it goes into. It's a fact of mathematics, and you can go back and double check this. I know I certainly did the first time that I saw this. But these exponential decaying synapses, if I have 2 inputs that increase it by a fixed algebraic amount, every time it bumps up by 0.01, let's say, that is going to generate the same total amount of current as if I had 2 separate synapses, that were being triggered. So this adds linearly, which is really a nice property. So I could have, even if I had, there's no difference between having 100 exponentially decaying synapses with the same property, or 1 synapse that's all getting the same input, that's all incrementing by the same amount. It's the power of math, people. And so obviously 1 is more computationally efficient than 100, though. So, okay, so I have a stimulus. I want to feed it into the cell synapse. So that's easy. I'm going to construct a netcon. And so my netcon is going to construct from my stimulus to my cell's synapse, right? And we use dot notation to indicate something that belongs to something. So this is the synapse that belongs to my cell object. And then every netcon has a weight. We've seen this enough times. and I happen to know, well, let's just say that I didn't happen to know. All right, so, 1 is a nice number to start out with, and it's going to have some delay because it takes time for things to happen. So let's say this has a delay of 1 millisecond. And then the way we get this going is we, record. All of this is sort of standard now, right? We're going to record the times. We're going to record the membrane potentials. So we construct the vector. We do the dot record. So now it's the cells, somas, centers, membrane potential. And then we can initialize this, our simulation. So this is just setting up, amongst other things, it's setting up the recording, it's setting up the membrane potentials, it's setting up the state variables to be at basically, so this means after you do that F initialize of -65 millivolts, I don't know if we've been clear about this, this is as if the cell has been voltage clamped to -65 millivolts for all eternity. And what that means in particular is the value of M that you'll have is the value of M infinity when V is -65. So it's not just setting the voltage, this is having the consequence of setting the other state variables. If you wanted to have a situation where you had a number of cells and different cells have different resting potentials, you can create an F initialize handler to actually set the potentials on each cell separately. You can look that up, or you can talk to me. I actually have an example somewhere. But in any case, here's our thing, and then we'd want to plot it. So we've been doing Plotly, so let's just do Plotly for a little bit. Import plotly.graphObjects is go. And then, of course, when we plot, this is all sort of old hat now, I hope. Fig is going to be go.figure, fig.addTrace, go.scatter, and we'll just specify that the X is T and the Y is V, and then we'll show it. And hopefully this will give us a nice little action potential. So let's find out. So I say Python ball and stick.py. And inconveniently, this pops up in another window. So let me, another monitor. So here we go. So a thing has happened. How do we feel about this guy? Why does our action potential look like this? Anybody?
It doesn't start at the steady state.
Well, it was, I mean, this is pretty steady. It's pretty steady. -67. But this, it jumps straight up, right? So I'm hitting this way too hard. Oops. So what I can do is instead of having a weight of 1, let's say it was 0.1. And now if I were to run this, what happens? Let's find out. Let's say ball and stick. Looks a little better. Still jumps up pretty drastically. All right, 0.01. There we go. This is looking a little more action potentially. Still kind of an abrupt start to this though. So let's dial it down even more. 0.001. Okay, not strong enough, right? Not getting an action potential. So 0.02. You can rerun it. There we go. So we see we don't have any sort of drastic, we don't want anything where it's super drastic or just jump straight up, which was a problem, incidentally, in the slides that I showed on Tuesday. I was hitting the cells way too hard and they looked very drastic. So this is strong enough to generate an action potential, but it's not so strong that the synaptic current is like dominating. Does that make sense? So this is another reason to play with a single cell. So now that I've played with the cell, I can see that the cell is doing reasonable-ish behavior. It looks like an action potential. All is well, right? This is much better than that, or really anything else that we saw. Right? This can be our action potential. We could tweak, we could play around with this. We could choose different synaptic weights if we want, but fundamentally it's basically working. All right, so we have our cell. One other thing that we ought to do with our cell, we ought to have our cell keep track of the times that it spikes, right? Because when we're talking about a single cell, it's very easy to look at time series. But if I'm talking about a network of cells, I don't want, 1,000 I don't want to look at 1,000 line graphs for the centers of 1,000 somas membrane potentials. Never mind their dendrites, never mind however, many different locations they have. All right, so I'm just going to say, what I really want to know is I really want each of these cells to keep track of its own times that it spikes. And so we can do this. We can do this pretty easily. We can create a netcon, right? And we saw that in general, you can use netcons to connect things. We're not going to connect anything together, but we are going to say that I want to monitor the center of my soma's membrane potential. It's not going to go anywhere. I do need to say this section. So section is equal self.soma. All right, I'm going to construct this netcon. It's just going to monitor a certain location. I'm going to construct a list. Let's say spike times is going to be a vector. All right, and then I'm just going to have my netcon record in a spike time. So every time that the cell fires, we'll just make a note and store it in spike times. And so how do we see if this works? Well, we see if this works by testing it, right? So let's just go ahead and have the cell print out. So print spike times are going to be the list of cell.spike times. Cool. So this will tell us as a list, these are the times that the cell spiked. It's only going to spike once in our test, but that's fine. It should be, well, depending on where the threshold is, let's say about 8.2, something like that. So we have a hypothesis. Before we even look at it, before we actually run it, we've made a check. So we know, we predicted what we should have before we run it, and that'll help us see if it's working. So I guess I can make this even bigger. So Python ball and stick, 8.25. Look at that. We called it pretty well, I think. So the cell knows when it's fired an action potential. And when we go into a network, we'll want each cell to keep track of its spike times. So are we happy with the individual ball and stick cell here? Now I'm going to show you a little trick, though. I don't know if you guys know this. We haven't done this yet. Make this bigger, even more. So right now I have all of this stuff is pretty generic, right? Here's class ball and stick. I'm defining what I want to have happen. But now down here, I'm no longer defining what a ball and stick should do. I'm saying, okay, here's my test. Here's my run. What I can do is the following. I can say if name is main, and I don't strictly, and then indent all of this stuff below it. And so what's going to happen, what this does is this allows me, so, well, let's just see. So if name is main, we're going to do this. So, and you'll notice before we had this thing called main. What that means is when I run a script from the terminal, I say Python ball and stick. That script, that file that I ran, gets this name of main. And so it's going to be true, and it's going to go, it's going to do the thing, it's going to make the graph, it's going to print out everything. Awesome. But, and here's the beautiful thing. Now I could just as easily, if I was in Python, I could say from ball and stick, because that was the file name, import ball and stick, which was the class name. And you'll notice it works. I now have a thing called ball and stick. I can create a ball and stick. There you go. There's ball and stick 1. All right. So now I could import from that file just the piece that I needed. It doesn't run any of the stuff inside this name is main bit, because name is not main. Right. I'm running something else. So I have a standalone program that lets me test the ball and stick, but it also gives me a thing that I can extract out of it, namely the ball and stick class, and I can use that to build a network. And then I could test the network, and I could do the same thing. So this is one way of giving you sort of modular components that have their own tests, and that you can test and you can run independently. All right. So anyway, so fundamentally, we've made a ball and stick. Awesome. We have our cell. It generates the action potential when given the synaptic input. Life is good. All right, but this is supposed to be a discussion on networks. All right. So how are we going to actually make a network of these guys? Well, we'll do it in a new Python file. Right? We'll leave the ball and stick alone, because now we're going to keep that. We're going to keep that level of modularity. We're not going to touch it unless we decide that we need something else, but I don't think we do. We're not going to go back and touch that ball and stick. That's a perfectly good cell. All right. But now let's build on that cell a network. Okay. Well, we want to use NEURON, so we'll do all of our usual from NEURON import age from NEURON.units. Let's grab some units. I mean, again, these are NEURON's default units, so it doesn't really matter. I'll save this. We'll call this network. And in particular, though, I'll say from ball and stick, I'll import that ball and stick class. And you'll notice it was kind enough to auto-suggest it, which is one of the great reasons to use like something like Visual Studio Code or an IDE to do your editing instead of just a plain old literal text editor. All right. Now I don't want to start out, and I'm not going to start out with parallel. Well, all right, let's just see what happens. Let's see how things go. So I'm going to create a network. My network is supposed to be a ring. So the idea is that cell 0 is going to send to cell 1, cell 1 is going to send to cell 2, so forth and so on until I get to cell n-1, which is going to send back to cell 0. All right, how are we going to do this? So let's build, just as we built the concept of a cell, let's build this concept of this circular network. And the reason for doing this, again, inside of a class is because now I could maybe create multiple of them of different sizes, and I could see how they interact. Imagine that I have a small one and a big one, and the big one sends inhibitory inputs to the small one, but otherwise they go, I could do all kinds of crazy things. So let's go ahead and create our network. So I don't want to call it network because that's too generic. So how about ringnet? And then every time that I'm creating it, fundamentally now it's going to have an identity, so the self. But now I really want to know, well, how many cells am I going to have? Cool. And let's do this. Let's do this. Let's say that, well, okay, I'm going to have that many cell IDs. So I'm just going to go ahead and construct this as, well, which GIDs do I have? I have obviously all of them. So it's going to be the range of it. So that means it's going to go 0, 1, 2, blah, 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 up to n-1. That's just which cells I have. I don't really have to do this, but I'm just going to split it out because it's going to make it easier when I do our parallel stuff. But in any case, what I do have to do is I'm going to have to construct all of my cells. Well, I mean, we've seen this before. So I'm just going to construct the ith ball, a list that consists of, say, the ith ball and stick, where I is sort of coming from these my GIDs. So I'm going to, if I'm going to, so my GIDs go 0, 1, 2 through n minus 1. So it's going to construct cells 0, 1, 2 through n minus 1. Well, let's just see. This is getting a little tricky already. So let's just go ahead and create one of these guys. And I'll make a ring net of 5. And what I can do, I can test this and go back here. All right. And now I see that network.py, and I can say python-i to give me an interactive thing. Python-i network.py. And when I do this, I should have a net. There's my net. You'll notice that it doesn't print out pretty because I didn't give the net a representation, but I certainly could. More to the point, though, the network has cells. And namely, since my net was a ring net of 5, let me move this over so you can see it. Since my net was a ring net of 5, sure enough, I see ball and stick cells 0, 1, 2, 3 through 4. Right, 0 through 4 is 5 cells. All right, so I'm constructing this. All is well with the world. Now I'm going to want to connect the cells together. Okay, so ideally we want cell 0 to send a signal to cell 1 to send a signal to cell 2, blah, blah, blah. What I'm going to suggest, though, is there are ways to do this without invoking a parallel context, but there's never really any advantage not to do this if you're willing to commit to having identifiers. And the informaticist in you ought to be loving identifiers. So we're going to do, what we'll do is let's create identifiers for everything. So I'll say, in order to do this, I'm going to need the parallel context object. So this is h.parallel context. This is not going to run in parallel just yet, but this is what's going to allow us to do these identifiers, to connect things by identifiers. And so there's two things that I have to do when I do this. So I'm going to have all of my cells. I need to tell NEURON that I own my cells, so that this identifier, cell 0, belongs to this current process. And this is actually a two-part step. So let's just do this. So for each of my cells, so for cell and self.cells, for each of my cells, I'm going to say two things. I'm going to do set GID to node. I'm going to say my cell's that cell's GID is going to correspond. So that cell's GID is going to live on whatever the current process is, which is PC.id. PC.id is who I am. So that cell 3, lives on process whatever. And then in particular, though, so now I know which computer, which processor, which core to ask about cell 3. However, I also have to be able to say, well, that cell's GID, what is the netcon that I'm listening to? How do I know if cell 3 is fired? Well, that cell GID, so 3, let's say, corresponds to that cell's netcon. So I now know these two lines collectively tell me cell 3 belongs to which processor, and when I'm on that processor, when I'm talking about cell 3, what netcon owns it? Or what netcon is the relevant netcon? That's the spike detector. And we've already tested our spike detector, and we know our spike detector works. So I have declared, so this is a little bit of boilerplate that you need for making parallel stuff possible, making numeric connections possible. But you don't have to be doing parallel, you're just doing for these numeric stuff. So now I'm the network. I want to create a whole bunch of netcons, and all of my netcons are going to connect the numbers to each other. So let's just say I'm going to create a list to store my netcons. Remember, in Python, if you don't have a reference to a thing, here, the netcons, self.ncs, let's say, if you don't have a reference to a thing, it doesn't exist. It's known as garbage collection. Okay, so I'm going to just build up my netcons. I'm going to have one netcon for each cell. The netcon that I'm interested in, though, because I already have a netcon that's a spike detector that's handling the presynaptic side. So now I'm going to think of myself as a post cell. So for a post cell in self.cells, and I don't have to call it post cells, but I really want to make sure that I remember that I'm talking about the postsynaptic side. So my current netcon, I'm going to construct a netcon, but I'm going to do it based on the number. And if I'm doing it based on the number, I use GID connect, pc.gid connect. I don't go h.netcon. I'm just going to say, I'm going to connect from a number. Well, what number am I going to connect from? 3 is supposed to get from 2. 5 is supposed to be postsynaptic of 4. 10 is supposed to be postsynaptic of 9, right? Everybody sends one more. So it's going to be the presynaptic side is going to be the postsynaptic side. Oh, sorry, it's post cell, right? The postsynaptic cell's GID less 1 is the one that's sending it over. And that's going to go to the postsynaptic cells. I got to remember to type post. It's going to go to the postsynaptic cell synapse. Except there's a minor nuisance here. Anybody see the minor nuisance? Well, if I'm cell 0,
What happens? Yeah.
Yeah, go ahead. Finish it.
No, I was talking about when you are circling back towards the end.
Yeah, yeah. So if I'm cell 0, there's a problem because there is no -1. So what we do to get a wraparound, and we saw this on Tuesday, I guess, is we use the modulus operator, which is the remainder. And so basically the modulus operator, every time I get to n, I start counting at 0. Right? So I go, you know, if I'm doing mod 5, I go 0, 1, 2, 3, 4. I would be 5, except now it's 0. 1, 2, 3, 4, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. And it works back, you know, so since that's the rule, -1 is therefore n-1. So you can think about it, but in any case, this is always going to be, it's the previous one, so it's literally -1, except for the case where it's 0, where it wraps around back to n-1. But that gives me my netcon, and my netcon can have a certain delay. And it doesn't really matter. The only property of the delay that matters, at least in, well, first of all, delay has to be non-negative because causality, right? You cannot have a postsynaptic cell respond to a thing that hasn't happened yet. But in particular, not only that, you in a parallel environment, the delay has to be strictly positive. It cannot be 0. This is what allows us to speed up simulation, not have to communicate every time that a thing fires. So in any case, and we saw from the previous thing that a synaptic weight of 0.002 was sufficient. And then once we're done, we have to remember to append the netcon that we create to our list of netcons. Because if we don't, it's going to go away, because the moment that we don't have a reference to a thing, it doesn't exist, because that's how Python works. That's how sort of any garbage collection language works. So every cell sends to the next cell. So then I can set this up, and then I can just go ahead and let's say that I've set this up. I want to initialize a simulation, so -65 millivolts. It'll do it everywhere because I haven't told it anything else. And now let's say that I want to run this for 200 milliseconds. And if I define millivolts in milliseconds, I have. All right, awesome. So now what I can do is I can loop through for cell in my network cells, and then I can just print out, let's say my cell GID, and the list of the cell.spike times, which is basically more or less a thing that we did the previous time, except now I'm looping over everybody. All right, of course, now if I run this, let's see what happens. I'm gonna take out that dash I. Cell 0 never spikes, cell 1 never spikes, cell 2 never spikes, and so forth. Why is that? Well, the answer is because I didn't give it anything that would make it go, right? I never stimulated the network. So everybody's connected, but if nobody's spiking, nobody's going to start spiking. So let's go back here and let's be lazy and let's say, hey, look, netstim, let's go ahead and copy our stimulus, our initial stimulus that got that first cell firing. We'll just copy it over. We're going to have to define this, obviously, before we initialize a model. So there we go. We'll have one extra stimulus. Starts at time 5 milliseconds. Sure, that's perfectly good as any. But now where does it go? There's no longer a thing called cell. It's actually net.cells 0. The first cell, the 0 cell, is going to receive that input. And so we have one event going to one cell. And now let's see what happens. Nothing good. Why is that? The synapse has a rate. Sincere question. Why is that? I'm confused now. That should have worked. Why did nothing happen? Let's just hit it harder.
Can we check if we got an action potential in the first cell?
Well, we didn't. I mean, you're absolutely right. The punchline is that we didn't get an action potential in the first cell. So what I did here was I dialed it up. So I had originally gotten an action potential with this value. So I'm a little bit confused why it didn't work over there. Did I change something? But in any case, if I hit it, if I hit that first cell real hard, well, let's go back. 0.002. Oh, you know what? I bet I didn't save. I bet I didn't save. If you don't save the thing when you make the change and add that stimulus, that will also cause it to not have that stimulus. Okay, so in any case, there we go. So our first cell we knew from before fires at 8.25, and then we see cell 1 is going to fire at 11.42, cell 2 fires at 14.57, 3 at 17.7, 4 at 20, and then a little bit later, cell 0 fires at 24, 1 fires at 27. So it just keeps wrapping around over and over again. So this is good. This is our network. It's not parallel. It's actually just a few lines away from being parallel. But you know, it would be great to actually see this, right? To actually see this in a graph. And so there was some code that I gave you on Tuesday. But so what we'll do is we'll import matplotlib.pyplot as PLT. You could do that. You could do really sort of anything else that you want. And I'm in fact actually just going to be extremely lazy and copy paste this from my solutions. But fundamentally, this is code that's going to generate a raster plot. So I'm going to loop over every cell. For every cell, I'm going to draw a vertical line. That's what V-lines is every time there's a spike. And so it's the GID minus 0.5 to the GID plus 0.5. That way it's centered at the value of the GID. Let's see what this does. Okay, you see that circle there? That circle means I didn't save it. Let's try this again. Saved, now it goes back. Now when I run it, there we go. So I see that cell, so here's the GID, here's the time. Cell 0 fires, then cell 1 fires 2, 3, 4, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. Everybody's a little bit after everybody else. And one of the other things that I want to point out here. All right, so this is all well and good. You'll notice, you may have noticed, right? I didn't hard code any numbers, you know. Well, I guess I hard coded a delay and a wait down here, but I didn't hard code the size of the network. So what I can do real easily is I could just say, well, you know what? I want that network to be a network of 10 cells. And then now if I run it, ta-da, now I'm seeing a ring network where the ring is 10 cells around. And everybody's a little bit further. Right? So what I've done is I've parameterized my network. And if you parameterize your network, you can test it in a small size and then scale it up to a bigger model. All right. And so one other thing that we can do here, yeah, and I'll just show you this. I don't know if you guys know this, but in Python, if I do import sys, sys, and then I can go down here and I'll do int, the integer value of sys.argv of 1. Nope, that's not a 1. Sys.argv of 1. And this goes back to ancient programming days in C, where there were variable numbers of arguments. That's what argv says for. And in C, there was an argc and an argv. But in any case, so what this is doing is this is going to grab whatever number that I type after network.py. Network.py is argv of 0. It's going to grab whatever number I type, and it's going to make a network that size. So here, for example, so now I can say, well, now if I run this, it's going to yell at me because there is no argument after that. But if I say, okay, give me a network of size 5, and I run it, and it does the ring network of size 5. But now if I want a ring network of size 50, and I run it, and there we go. It goes up, 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 and then starts over. And I'm only running it to time 200, so we don't see very far. All right, but we've parameterized it. We've given this nice little interactivity so we can see it. Like I said, it's actually just a few lines from here to what's in the zip folder as network4.py. But I do absolutely have a hard deadline today, so I am going to have to stop it here. But we do have a working network. We'll finish the parallelization of this on Tuesday. It won't take long. Does anybody have any really quick questions on any of this? Okay, hearing none. Let's go ahead and call it a day. Like I said, on Tuesday, we'll, I guess, go over Ted's gave new homework. So we'll finish this, and then we'll talk about Ted's homework, and then we'll move on to some more didactic material. I hope everybody has a wonderful weekend. Thanks all.
Thank you.